all of this works in the situation where my data flow graph is feed forward. So the natural question that arises is, what happens if I have feedback in my circuit? How should I handle it? So an example of that is, right, something like this. Let us say dA is equal to 1, dB is equal to 1. The iteration period bound in this case is going to be how much? This has a loop, therefore there is an iteration period bound which is not 0, and in this case it is going to be how much? 2 time units. What is the critical path through this? Also equal to 2 time units. It is basically the delay through A and B. In other words, if I was directly implementing this using hardware and that delay element was implemented as a hardware register, then the propagation delay through A plus the propagation delay through B is the critical path. So my critical path has now become equal to iteration period bound. It looks as though I really can't do anything to improve this, and that is correct. I cannot do anything to improve this. Okay, that is the whole point of defining that iteration period bound. There is nothing as such that I can do. There are some tricks that may be applicable under certain conditions, but in general for a signal processing application you can't do anything further. The moment your critical path has hit your iteration period bound, that's it. You might as well stop trying to improve on it. If you are not meeting your throughput constraints, you need to relook at your algorithm or your hardware technology itself. Now, even though this has already hit the critical path, there is one thing that we can observe from this which is useful to understand, which is that this and this, I mean the two graphs that I have drawn over here are essentially the same except for the delay unit. And what we can essentially say over here is that one is a so-called retimed version of the other. What I mean by retiming, in other words, is, let us say that I had a functional node which looks like this and it has a delay on its output. These two I claim are essentially the same thing, which is pretty much what I started off with at the beginning of this lecture by saying that time invariant systems, right. The fact that I have shifted a register from the output side to the input side does not change the functionality that is finally going to be observed. If this condition is true, then we can actually generalize the idea of pipelining somewhat, because now I can basically look at isolated nodes and decide whether or not I can move registers across them. In particular, I can extend this further and say that supposing A had some number of inputs and some outputs, and let us say that it had registers, at least one register on each of its inputs, or just for clarity let us also add one more register over here. A retiming step could involve something like this. I will take one set of registers from each of these, from input nodes, and put them to the output. So what would happen is, on the output side I would end up with one register on each of the output edges. On the first incoming edge to A, there was one register to start with, now there will be 0. On the second one there were 3 to start with, that reduces to 2, and on the third one there were 2 to start with, that reduces to 1. So the claim is that these two versions of the graph are exactly the same, they are performing the same computation. Okay, and anybody who is outside of this box that I draw over here cannot tell the difference, right. Anybody who is observing it from outside this boundary cannot tell the difference that there has been some movement of registers around the functional units inside. And that is actually quite a powerful claim, because effectively what it's telling you is you can now look at a part of a graph, do some retiming on it without having to worry about what the rest of the graph looked like. Okay? And the fact that you have made this isolated change over here can in turn impact the critical path through the entire circuit.